Beyond addition and multiplication, from exponentiation and recursion to topology, learning, and survival. Number 1696, June 22, 2026. Gerald C. EclaireMD Foundation. Category, Self-Reflection. Mathematics, Learning, and Life Trajectory. Preface for readers: eat more protein and fresh vegetables. Eat less red meat and processed food. Reduce portions if overweight. Eating a little less will not hurt you. Overeating for years will. Exercise daily. Walk at least 7,000 to 8,000 steps. Drink 85 to 100 ounces to 0.5 to 3.0 liters of water daily. Sleep 6 to 7 hours each night. Manage stress. Avoid draining people and unnecessary conflicts. Put your health first. Wealth, fame, and power mean little without health and life. Introduction. After completing my article Multiplication, not Addition, from Arithmetic through Newton's Law of Motion to a Lifetime of Learning No. 1695, June 22, 2026. I found myself asking a new question: if multiplication captures interaction, what mathematical operation captures nonlinear feedback itself? Is it exponentiation? Is it recursion? Is it topology? Or is it something else entirely? At first glance, these concepts appear unrelated. However, after reflecting on my own medical research journey, I began to see them as different layers of the same developmental process. What started as a simple question about arithmetic gradually evolved into a broader question regarding learning, knowledge accumulation, and life trajectories. Level 1 Addition and accumulation. Addition is the simplest operation most of us learn during childhood. A plus B plus addition represents accumulation. The individual components remain largely independent. Examples include money deposited into a bank account without interest. Other examples are the total distance walked over many days, or the number of books read during college years. The process is linear. One item is simply added to another. Addition builds collections. Level 2 Multiplication and interaction typically introduces a fundamentally different concept. A times B times variables no longer remain independent. Each variable influences the overall outcome. Examples include money deposited into a bank account, earning simple interest. One of the most famous examples is Newton's second law of motion. F equals m times a force is not mass plus acceleration. Force emerges from the interaction between mass and acceleration. The same principle appears in my TSI model. TSI varies as glucose times pp times pulse pressure. Systolic blood pressure and glucose do not act independently. They interact simultaneously within the same physiological system. Multiplication captures coupling and interaction replaces simple accumulation. Level 3 Exponentiation and compounding. Expansion introduces another layer, i.e. growth influences future growth. Examples include money deposited into a bank account earning compound interest, population growth, epidemics, and rapid learning curves. A small difference at the beginning may produce a very large difference later. Exponentiation is often the mathematical signature of positive feedback. Compounding replaces simple interaction. Level 4 Recursion and self-transformation. As I continued reflecting on this hierarchy, I realized that recursion may be even more important. X equals fx, where t equals 0, 1, 2. A recursive system acts upon itself. The output becomes the next input. Examples include learning, evolution, neural networks, and scientific discovery. When viewed from this perspective, my own research process over the past 26 years appears fundamentally recursive. Paper No. 1695 depends upon paper No. 1694. Paper No. 1694 depends upon paper No. 1693. Each paper contains knowledge acquired from previous papers. More importantly, each paper changes the researcher who writes the next paper. The process is therefore not simply the production of documents. It is the continuous transformation of the investigator. Recursion captures self-transformation. Level 5 Topology and Trajectory. Topology represents a different kind of concept. It does not directly describe feedback. Instead, it describes the structure through which feedback operates. Examples include attractors, spirals, bifurcations, phase space trajectories, and the viscoplastic topology VPT trajectory models that I have developed during the past 6 years. Topology answers a different question. Recursion tells us how a system changes itself. Topology tells us where that changing system travels. In this sense, topology becomes the geometry of development. The shape of the journey becomes as important as the individual steps. A hierarchy of learning. This line of thinking suggests the following hierarchy: addition gives multiplication gives exponentiation gives recursion gives topology, where addition equals accumulation, multiplication equals interaction, exponent equals compounding, recurrence equals self-transformation, topology equals trajectory. Geometric level builds upon the previous level while introducing a new layer of complexity. My own medical research journey. When I apply this conceptual framework to my own health journey involving chronic conditions, mortality-related diseases, and expected lifespan, I realized that my paper No.1695 primarily explored the initial transition from addition operation to multiplication ocean theory. In my earlier work, I viewed the body as a collection of separate food storage silos. Over time, however, I came to view it more as an integrated food processing factory, where multiple physiological variables interact continuously with one another. This shift from accumulation to interaction fundamentally changed the math physics view I understand metabolism, disease progression, and health outcomes. However, my broader research journey is more accurately represented by recursion. Knowledge is equals F. Knowledge is where n equals 0, 1, 2. Every paper changes my understanding. The modified understanding influences the next paper. This cycle then repeats, after thousands of iterations. The resulting trajectory no longer resembles a straight line. Instead, it begins to resemble a spiral-like topological path, where previous knowledge continually reappears at higher levels of understanding. This mathematical process becomes both recursive and topological. Multiplication explains interaction, exponentiation explains compounding, recursion explains lifelong learning. Topology preserves the shape of that learning journey. Conclusion: the original question was simple: what mathematical operation best captures nonlinear feedback of medicine? The answer may depend on which aspect of feedback we are examining. Addition describes accumulation, multiplication describes interaction, exponentiation describes compounding. Recursion describes self-transformation. Topology describes the trajectory created by that transformation. Conclusion: the original question was simple: what mathematical operation best captures nonlinear feedback of medicine? The answer may depend on which aspect of feedback we are examining. Addition describes accumulation, multiplication describes interaction, exponentiation describes compounding. Recursion describes self-transformation. Topology describes the trajectory created by that transformation. Viewed from this mathematical perspective, lifelong learning may not be adequately described by any single operation. Instead, it emerges from the combined effects of interaction, compounding, recursion, and trajectory evolution over time. Epilogue: returning to a simple question while writing this article, I found myself returning once again to elementary arithmetic. Most people learn addition, multiplication, exponents, and other arithmetic operations during childhood. Few of us ever stop to ask what these operations truly mean or what they represent in the real world. My recent work on TSI, VPT, and life trajectories has gradually led me back to this question. The more I study biomechanics, including psychology, personality disorders, pathophysiology, neuroscience, disease protection, and human development, the more I realize that arithmetic operations are not merely computational tools. They often represent different forms of reality. Addition accumulates. Multiplication interacts. Exponentiation compounds. Recursion learns. Topology remembers the shape of learning after nearly 80 years of life. I find it both surprising and satisfying that some of the deepest questions I encounter today can still be traced back to IDs first encountered during childhood arithmetic lessons at age 6. Knowledge often begins with complexity, and understanding frequently returns to simplicity. Knowledge is the ultimate power in life and the foundation of human progress, survival, and the continuous advancement of civilization. This article highlights a universal truth found in many advanced fields: complexity is often a stepping stone on the journey back to profound simplicity. True mastery is not achieved by making things increasingly complicated, but by discovering the deeper meaning hidden within simple concepts. After decades of studying mathematics, physics, engineering, psychology, medicine, neuroscience, and topology, I find myself returning to the elementary arithmetic operations first encountered during childhood. The difference is that I now see them through a very different lens. A simple multiplication sign is no longer merely an arithmetic operation. It represents interaction, coupling, amplification, and the interconnected nature of complex systems. In this sense, knowledge often begins with complexity, while understanding frequently returns to simplicity. The most fundamental concepts sometimes contain the deepest truths. This content is provided for educational reference only and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and its related materials belong to the author, Gerald C.